I want to talk about concentration-dependent parameters in the electrochemical simulation. And this can be quite important in some cases. I just want to motivate this with an example from literature. So here you see a study from NMC 622 cathode half cells, and there were C-rate tests at different C rates. That is these points here. And you see that especially at high C rates, the voltage drops quite fast towards the end of the discharge. And in this study, there were also electrochemical simulations performed. That is the lines. And if you want to get a quantitatively comparable simulation result to the experiment, then it can be necessary to consider the lithium concentration-dependent properties of the active materials and of the electrolyte. And this is actually the reason also for this very fast voltage drop towards the end of the discharge. And I want to show you now how you can set up a simulation with GeoDict 2025 using the lithium concentration-dependent parameters. And there are two different kinds of materials that have or can have lithium concentration-dependent parameters. First, there are the active materials. And for the active materials, the lithium diffusivity and also the electronic conductivity can be depending on the lithium concentration inside of the active material. And you can set up this in the simulation by using an expert setting. And the other component in the battery that can have concentration-dependent parameters is the electrolyte. There it can be the ionic conductivity, the diffusivity, or the transference number. And here you can set it up in the graphical user interface. And I just want to mention that this is at the moment possible if you use the best solver in BatteryDict simulation. And we are working that we want to implement it also for the LIA solver, so the other solver in BatteryDict. And let's get a bit more specific for the example I mentioned before. So we have a cathode with NMC 622. And if you look on the data for the diffusivity of the lithium ions inside of the NMC, you can find such a property as a function of the lithium concentration inside of the lithium particle. And you can see that if you have a low lithium concentration, then the diffusivity is around 4 to the power of minus 15 square meter per second. But here, when the lithium concentration is very high, then this diffusivity is dropping strongly, and it's 1 order of magnitude less than at this lower concentrations. And the first challenge is to get this data for your simulation. And you need to rescale it. So you need the data as a table in a text file. The first column is the lithium concentration, the removable lithium concentration that is between 0 and Cmax. And the other would be the diffusivity. And if you want to know how you get these text files. We prepared for many of the active materials that we ship with GeoDict the text files already. You can just write to support@math2market, and then we can send you this. And also we have PDF instruction that we can give to you if you measured your own material in the lab and you want to know how do I set up the text file, then yeah, you can also ask us and we can provide it to you. And after this, I want to show it how this looks in GeoDict. So I open GeoDict 2025. And first, I want to open the structure. It's a cathode structure that I created with one of the structure generator GeoApps in GeoDict. I change the colors a bit. So we have 3 phases. We have NMC 622, the active material in gray, the CBD network in red, and the pore space that is filled with the electrolyte. And I already created a charging curve using the homogenized model. And yeah, it looks like this. So it was starting at around 3.9 volts and then discharging until 3.4 volts. And the charge rate here was 3C, so it's quite fast discharging. And this is how the discharge curve looks like when you use constant parameters for the diffusivity of the NMC. And here we see this looks a bit different than in the experiments because this voltage drop in the end is not so strong. And now I want to show you how you can do this simulation when you use the lithium concentration dependent diffusivity. And for this, I have the file with the concentration dependent diffusivity prepared already. So it looks like this. It's just what I showed before in the PowerPoint file. So the first column is the removable lithium concentration. It moves between 0. So this means it's fully delithiated and you have the highest OCV voltage towards the Cmax value of the NMC 622 with 33,000 mole per cubic meter. And in the second column, you have the diffusivity values for all the different lithium concentrations. And you take this text file and you can copy it to your project folder. So that's the project folder of GeoDict. And we will soon need the file name of this text file. So I copy it already. Good. So now we need to set up the expert setting that in the next charging simulation, we use the concentration dependent diffusivity from this text file. And for this, you go up here in top to settings and then edit expert setting. And here you need to first name the command that you are using. We are now using electrode charging. So it's charge electrode command in the BatteryDict module. So first I select here BatteryDict module. And then here the charge electrode commands. The same would be if you do a full battery, then you would select charge battery. And here we need the key cathode active material 1 lithium diffusivity file. Because we have only one active material, of course, you can also have an electrode with different materials. Then you can also provide different text files here. And in the end, I enter the file name of our text file. because I copied the file into the project folder, it's enough just to provide the file name here, but just to mention, you could, of course, also provide the file path if the file is in another folder, or also relative path is supported here. And then you just click OK. And now GeoDict knows when it's performing the next charge electrode command that it will use this concentration-dependent diffusivity. So what I can do now is I just load the settings from my first simulation into GeoDict. So I click here in the result viewer to load input parameters. And then all the parameters from the first simulation are taken over. I go to battery dict and then electrode, charge electrode. When I open the settings here, we see the different configurations. So that's the materials we are using. And here it's just as before, we have 3C charge rate, so quite fast. And the simulation is stopped at 3.4 volts. And we are using the homogenized model just because it's faster now here in the live demonstration. But I will change here the result name that we can differentiate to the original result. So I say the result, this is with concentration-dependent diffusivity of the NMC. And then we are done here. So I click OK and then charge. Yeah, now it will start. To first calculate the effective parameters for the homogenized model. It's just what I said in the first talk. So here it's now calculating the effective conductivities. And after this, it will calculate the effective diffusivity and so on. And for the diffusivity, it will take now the concentration-dependent values that we provided in the text file. Okay, so it's done with the conductivity. Now it's calculating the diffusivity. And just to mention it, you can also use this with concentration-dependent electrical conductivity. Then you have a text file with the concentration information in the first column and the electrical conductivity of the NMC in the second column. But this only works with a fully resolved model because you need, of course, the information of the local lithium concentration inside of the particle, and that is not possible with a homogenized model. Yeah. Good. So should soon be finished, I think. Still calculating the conductivity. Yeah, this is running on the laptop, and yeah, I know always when I have teams running at the same time, it's a bit slower than when I run it before, yeah. So it's about double runtime when Teams is running at the same time. It also works in 2024, yeah. So since 2024, we have this feature. Okay, now it's done with the effective parameters, and now it's running the P2D model, so calculating the charging curve. And this is actually quite fast because it's the 1D problem only. And yeah, now it's done. And if you click both results here and this sync tabs, you can have a look here. And you already see this voltage drop towards the end of the simulation is much more prominent. And if you want to compare it, you can also click here, combine results. And here you see it quite clear that here in the end, towards low voltage, when the NMC is close to fully lithiated, you have less diffusivity and faster drop of the cell voltage. When you look in the Overpotentials tab, you can see that the difference is mainly here to the diffusive overpotentials. So I can only show this. Oh, that was one. It was resistance here, diffusive. So yeah, here you see the difference. So towards the end of the simulation, with the concentration depends, so that is this curve in dark blue, the overpotential is much more prominent than when you use the constant diffusivity. Yeah, and that was already everything I wanted to show. You can do the same with a fully resolved model, also using concentration-dependent properties in the electrolyte. And yeah, this is very helpful if you want quantitative comparison between experiment and simulation. Then very often you need to consider this more complex setup with the concentration-dependent properties. Thank you very much for the attending the session, also you online, and there will be now a kind of poll in the chat, so you can give feedback when you are online, how you liked the conference so far. And yeah, thank you very much. There's time now for discussion or have something to drink. Thank you.